So now let's do an example with a Young's double slit experiment. So imagine that we have a light source with coherent light. So all the light has a wavelength of 655 nanometers, and it's incident upon these two slits. And we have a screen over here. The screen's a distance of 1.25 meters away. And let's say that our two slits are separated, the center of one slit to the center of the other slit, by 2.85 micrometers. And so I want to know several things. First of all, I want to know the center spot, what we call the first order spots, second order spots, and then I want to know how many spots do we actually get? You know, what's the last spot that we get in here? And so how many spots? So I want to know the total number of spots. Okay, bright spots, that is. Okay, because what happens is, as the light goes through, it spreads out, and there'll be a bright spot right in the middle, and then we have destructive interference, it's dark, and we have more black bright spots, more black bright spots, more bright spots. So I want to know the total number of spots. I want to know, Y1, Y2, how far are these spots away from each other over here? We can even do Y3, okay, and so forth. So I want to know all these different things. So first thing is, we know that constructive interference, so the bright spots, that means constructive interference. Okay, so constructive interference means that sine theta, d sine theta, equals m lambda. So the possible sine thetas are m lambda over d. Obviously, m equals 0, theta equals 0. That's the central spot. So now, sine theta equals m lambda over d. Let's let m equals 1. So theta is going to be the inverse sine lambda over d. So that'll be the inverse sine of 655 nanometers divided by 2.85 micrometers. And so theta is going to be 13.3 degrees. So the first spots are at theta equals 13.3 degrees. And so we've got here 0 point, so 13.3 degrees, and it's 13.3 degrees either direction of the 0. So it's going to be both of them. So y is going to be, this is distance x, that's y, so y equals x tan theta. And so if you plug in 13.3 degrees, and then we know that this was 1.25 meters, I gave you that earlier, that means it's at 29.5 centimeters plus and minus. So that's going to be two spots, one spot up, one spot down. And so we have these two spots right here. That was y1. So now what about y2? That's going to be when m equals 2. Okay, so now sine theta equals m lambda over d. Okay, so theta 2 is going to be the inverse sine of 2 lambda over d. All right, so that's going to be 2 times lambda, which was 655 nanometers, divided by d, 2.85 micrometers. Okay, so that turns out to be 27.4 degrees. Notice it's not exactly double the other angle. Okay, and so if you plug in that y equals x sine theta, we get y is equal to 64.7 centimeters. Again, it's going to be plus and minus. Okay, so that's Y2. And so now we have our slit. We have here the central spot. That's going to be M equals 0. We have spots here. M equals 1, M equals 1. We have spot there. M equals 2, M equals 2. We could do this for the next one as well, and the next one. But the question is, how many spots do we get? Now, one possible strategy is just keep going. Have M equals 3, solve it, M equals 4, solve it, M equals 5, solve it. Eventually, you're going to get the point where it's not solvable, and then that means you've gone past the number of spots. Okay, so that's the long way to do it, because sometimes you can get, 4 or 5, M up to 4 or 5. Sometimes M can be hundreds, and so that would be hundreds of spots. Well, you don't want to spend all the time doing that. So remember, sine theta equals m lambda over d. So the angle is going to be the inverse sine of m lambda over d. Well, right away, this is your clue. M lambda over d, if we're doing the inverse sine of it, that cannot be bigger than 1. So if we just set m lambda over d equals to 1, that would give you the max m. So in that case, m equals d over lambda. For our case right here, that would be the d, 2.85 times 10 to the minus 6 meters, divided by lambda, which is 655 times 10 to the minus 9 meters. What you get is m equals 4.35. Well, you cannot have a fraction of a distance. So m equals 5 is too much, and so the biggest you can get is 4. So that means that m max is 4. Okay, so how many spots do we have? Remember, we have one spot at m equals 0. If m equals 1, we got a spot above and a spot below. So that means it's 2 spots. So for m equals 2, that's also 2 spots. So what does this do? It means that m equals 4 means 8 spots above, 1, 2, 3, 4, 8 spots below, 1, 2, 3, 4, and 1 spot in the middle. So that means a total of 9 spots. 9 bright spots. 1 in the center, 4 above, 4 below the center. And so that would give you the answer. Now, one more thing. We said we had that m max was equal to 4.35, and we said that that's 4. What would have happened, hypothetically, if m max was equal to 4.97? So m max is 4.97. What is that? That's still 4. Because that means you cannot get to 5. If you cannot get to 5, you don't get to 5. So that means it would still be maximum of 4 spots. And so this is one of these cases that you cannot round up. So you have to always round down, because this is telling you what the maximum is, and it has to be an integer. So the maximum integer is 4. So I hope that helps. That's going to be our example for Young's double slit. One of the next things we're going to discover, though, is that you can actually get self-diffraction in some sense with just one slit.